Lecture 6.5, Day 2, Logistic Growth. We have used the exponential growth equation y equals y sub 0 e to the kt to represent population growth. The exponential growth equation occurs when the rate of growth is proportional to the amount present. If we use p to represent the population, then the differential equation becomes dp dt equals kp. The constant k is called the relative growth rate. We have dp dt divided by p equals k. The population growth model becomes p equals p sub 0 e to the kt. However, in real life, populations do not increase forever. There is some limiting factor such as food, living space, or waste disposal. There's a maximum population or carrying capacity, M. A more realistic model is the logistic growth model, where growth rate is proportional to both the amount present, P, and the carrying capacity that remains, M minus P. The equation then becomes the logistic differential equation, dp dt equals kp times m minus p. We can solve this differential equation to find the logistics growth model. Once we solve it once, then we can just use the formula, and we don't usually have to solve it over and over again. Starting with the logistics differential equation, we have dp dt equals kp times m minus p. We notice that it's a separable differential equation, so we separate the variables. Now we can use partial fractions to help with our integration. 1 over p times m minus p should be equal to a over p plus b over m minus p. Clearing the fractions gives us 1 equals a times m minus p plus bp, and then we eliminate the parentheses. Now we separate the terms. For the m terms, we get 1 equals a times m, or 1 over m equals a. And for the p terms, we get 0 equals negative ap plus bp, or ap equals bp, so a equals b, which means 1 over m equals b. One over m, remember, is a constant, so we have 1 over m times the quantity 1 over p plus 1 over m minus p dp equals k dt. We move the m to the right-hand side, and then we integrate both sides, giving us ln p minus ln m minus p equals mkt plus c. Combining the logs gives us ln p over m minus p equals mkt plus c. Now we exponentiate both sides to eliminate the natural log. and I take the reciprocal of both sides. Notice on the right-hand side, we find the reciprocal by changing the exponents to negatives. This allows us to separate the fraction on the left-hand side, and p divided by p is 1. Then we add 1 to both sides. Solving for p gives us m over 1 plus e to the negative mkt minus c. Then we can separate e to the negative mkt and e to the negative c, so it becomes multiplication. Now since e is a constant and c is a constant, we can relabel this constant. We'll let a equal e to the negative c, and that gives us p equals m over 1 plus ae to the negative mkt. This is the logistics growth model. P equals m over 1 plus ae to the negative mkt. Here's an example of use of the logistic growth model. 10 grizzly bears were introduced into a national park 10 years ago. There are 23 bears in the park at the present time. The park can support a maximum of 100 bears. Assuming a logistic growth model, when will the bear population reach 50, 75, or 100? Starting with our equation, we have p equals m over 1 plus ae to the negative mkt, and we were given that m is 100. M, of course, is the maximum number of bears or carrying capacity. We also know the population at time 0, p0 is 10, and the population at 10 years is 23. At time 0, the population is 10. So when we set up our equation, we've got 10 equals 100 over 1 plus a e to the 0. E to the 0 is, of course, 1. That gives us 10 equals 100 over 1 plus a, or 10 plus 10a equals 100. 10a equals 90. A equals 9. So now we have one of the two constants we needed. And the equation becomes p equals 100 over 1 plus 9e to the negative mkt. After 10 years, the population is 23. So we have 23 equals 100 over 1 plus 9e to the negative 100k times 10. Notice that this time we filled in 100 for m in the denominator, which we had not bothered to do before, and we put in 10 for t. So we have 1 plus 9e to the negative 1000k equals 100 over 23. 9e to the negative 1000k equals 77 over 23, because we subtracted 1 from both sides. e to the negative 1000k equals 0.371981. Obviously, we move to the calculator in this step. Now, since we have an unknown in the exponent, we'll take the log of both sides, which eliminates the e, and we get negative 1000k equals negative 0.988913. And solving for k, we get k equals 0.000098891. Our equation then is p equals 100 over 1 plus 9e to the negative 0.1 t. And we got this 0.1 by multiplying 100 times k and rounding to one significant digit. We can graph this equation and use trace to find the solutions. We see that y is about 50 at 22 years. There would be 75 bears at about 33 years. And it would take 75 years to round to 100 bears. Now, because we're talking about bears here, none of these figures are exact. It's only a best estimate, so we certainly can't round to more than the nearest whole bear.